Another example. This time we will apply the properties of similar figure in and solving for an unknown side. Now, a surveyor wants to use similar triangles to determine the distance across the lake, as shown at the right. Part A. Are the two triangles in the figure similar? Justify your answer. Part B. What is the distance D across the lake? So now, one of the most common application of similar triangle, similarity in general, and similar triangle in particular, is in the use called indirect measurement. That means using similar triangles, we can find the unknown distance between two inaccessible locations. In this problem, for example, instead of swimming across the lake to find the distance D across the lake, the surveyor wanted to use the properties of similar figures. But first of all, we need to establish that the two triangles you're basing off your measurement are similar. Now let's do number one, part A. Part A. Are the two triangles in the figure similar? Now let's look at the two triangles. We have two triangles. One is smaller than the other. We have the given measurement in one. We have a side that is 300 feet and another side which is 50 feet. And then on the bigger triangle, we have a side that measures 120 feet, an unknown side. And then also we have a pair of angles that are congruent. Now, looking at the figure, you may be looking at it, and those of you who are my favorite students already are looking at these two angles, and you are screaming, vertical angles, vertical angles, vertical angles. They are congruent. Yes, they are congruent. You're right. I'm with you. Now, already you may be thinking to yourself, well, those two triangles are similar by angle-angle similarity. Again, you're right also. That's enough to justify that the two triangles are similar because they have two pairs of corresponding angles that are congruent. But for the purpose of continuity of our lesson, since we're talking about non-rigid motion, a composition of rigid transformation, rotation, translation, reflection, composed with a dilation, to justify two figures to be similar, let's look at whether or not we can use that as our justification. Can we identify composed transformations, including a dilation, to map one triangle onto the other? So first of all, what we can do here is we can rotate one of the triangles, the smaller triangle, by an angle of 180 degrees. Why is that? Because you can see that, okay, this side right here, this 50, let me use green, okay, this 50 feet side, if you rotate that 180 degrees, 180 degrees up to there, 180 degrees, that will fall flat on this side right there. Let me just approximate this side. And also we can rotate. If we rotated that, it will, remember, we are rotating the entire triangle, not just the side. And rotation is a rigid motion. Rotation maintains the angle and the measure of the angle and the side lengths. So this angle here will follow suit. It will be right there. Side, not angle, right there. And of course, the other side, this side right there, okay, will still be that side. So now we will transfer, okay, we'll transfer our measurement. And remember, this angle is still 75, that angle right there, because we just rotated. Remember, in rotation, side lengths are preserved, angle measure are also preserved. So now let's identify the relocated measurement. So let me just erase this indication that we rotated, and let me put in our lengths here. So this is 50 right there, which is actually this. No, I mess it up. Okay, that 50 right there. Let me just. Okay, that 50 is the same as this 50 right there. Also, this 300 feet, this 300 feet is the same as this 300 feet here. 300 feet. Now, what else do we know? 300 feet. Okay, what else do we know? We know that since this angle is congruent, okay, this angle right there, this angle, let me just color it. Okay, this angle is congruent to this angle, and this angle is congruent to itself. This third angle and this angle must also be congruent, because the sum of the angles of a triangle is equal to 180 degrees every time. Now, what does that tell us? So number one, we have done one rigid motion already, and that is the rotation, a rotation of 180 degrees. Now, question is, can we do dilation? The answer is yes. Okay, seems to me that since this angle right here, which we color coded, okay, this angle is congruent to this angle. Now, also this angle is congruent to that angle. So this side is parallel to this side. So if we dilate this point, that, let me see, this point and this point from the center, this point will eventually match that point. This point will eventually match this point. So we can do a dilation. So let's write it down. A dilation. Now the thing is, we have to identify the scale factor. Remember, the scale factor is the ratio between the side of the image, the length of the image, to the side length of the pre-image. In this case, we have two available measurements that we definitely know for sure. That is, okay, this side right here is 50, which is our pre-image, and we say we want to dilate 300 feet to fit to D. So we are going from smaller to larger. So our image is gonna be this, which is 120. So our scale factor, the scale factor is equal to, well, the length of the image over the length of the pre-image. That is 120, okay, over 50. Okay, let's just get rid of the zeros there. So you have the scale factor is 12 over 5, which actually simplifies to 2.4. So the scale factor is 2.4. So after doing a rotation, we can do a dilation with a scale factor of 2.4. All right, so for part A, our answer is yes, they are. Yes, they are. Yes, they are. Because we have a composed transformation that involves a rigid motion, the rotation, right there, and a dilation. So let's tell our story. Okay. Yes, because. Okay. Because the smaller triangle the smaller triangle can, oops, not can, can be mapped onto the bigger triangle, by let us do our mojo here. Okay, it's a composition of a dilation of 2.4 composed with a rotation of 180 degrees. Okay, so we understand this by now, that it results in the image of the smaller triangle by a dilation with scale factor of 2.4 composed with the rotation of 180 degrees. All right, so that's our justification for part A. Okay, take note that our information must be complete. We say rotation by how many degrees? We say 180 degrees, followed by a dilation. What is the scale factor? Okay, the scale factor is 2.4. We assume that the center of dilation, the intersection of the two lines, is set at the origin. So we have this 2.4. All right, so that's our complete answer. Now part B is asking us, now that we know that the two triangles are similar, can we use that fact to find the length, the distance d? D is equal to what? Okay, well, by a scale factor, okay, of course we can use the ratio and proportion between the sides. I know you can do that, but we can use the scale factor. In order to get 120, we multiply 50 by the scale factor, that is 2.4. All right, so we can do that also. So D must be equal to, if we are to find the dilation of 300 feet following the same scale factor, D must be equal to 300. Okay, 300 feet times, what's the scale factor? 2.4. And that will give us, okay, 300 times 2.4 is gonna be 720 feet. All right, how did I do that? 720 feet. Okay, so D is equal to 720 feet, which is the image length of 300 feet under a dilation with a scale factor of 2.4. And of course you can do that, alternatively you can do that using ratio and proportion. We can say 120, okay, 120 over 50. Okay, that's our answer already. Okay, I'm just showing you another way. 120 over 50 must be equal to, because of similar triangles, D, bigger to smaller, D over 300. Okay, and we can say 50D is equal to 120 times 300 is 36,000. Of course, we are dividing by 50 and dividing by 50. If you do your division, of course, okay, check my answer. The answer is gonna be 720, the same thing. All right, okay, so we have done enough example already. I hope you find these examples helpful. All right, don't be a slacker. Do your work. Toodles.